Virtual Research Café 10.0. I'm Frank Gomez, Executive Director of STEMnet. Behind the scenes, we have Monica Alacon, Admin Analyst for STEMnet. Much thanks to her for working the logistics and in publicizing today's event. The goal of the Café is to help foster research collaborations across the CSU and catalyze the submission of potential joint proposals. The Café brings together 3 CSU assistant professors to share their works in a relaxed setting for 10 minutes, reason for the 10.0. We hope you'll find opportunities for collaboration and or learn about a new area of research that you may impact your own program. Feel free to contact any presenter in the chat box when they're not presenting. At the end of the 3 presentations, we'll all come together to answer your questions. I will also be monitoring the chat box to call questions from the audience. So let's begin. Once again, we have 3 wonderful speakers presenting a snapshot of their work. Our first speaker is Santosh KC from the Department of Chemical Materials Engineering at San Jose State University. Santosh, the floor is yours.
Hi, everyone. Thank you for invitation. I'm Santosh KC, an assistant professor at Chemical and Materials Engineering at San Jose State University. Today, I'm gonna give you one of my research area on 2D materials, mainly focused on surface and interface properties of 2D materials. So before going into details, I'll just give you briefly my personal introduction. So originally, I'm from Nepal. I came here around 12 years ago as a grad student. And I live here with my wife and 2 kids. I have a 6-year-old daughter and I have 2-month-old son. So he's keeping us very busy recently. And regarding my activities, I like hiking and traveling, but there is not much travel this time, but I have been doing hiking regularly. The last hiking was this weekend, last weekend, and family vacation, not that far away, but Lake Tahoe, which is not that far from San Jose. And about 2 years ago, we visited Nepal, and it was a lot of fun. Regarding food, I like anything vegan or vegetarian. All right, so let's continue my research background. I did my PhD from University of Texas at Dallas. My background is computational condensed matter physics or materials physics. So I have research experience in 2 different areas, electronic device application side and also energy storage, such as lithium-ion battery. And then I did postdoc at Oak Ridge National Lab and University of California, Santa Barbara. And I work on transparent conducting oxide and also complex oxide, tuning electronic and optical properties of those oxide. And I have some experience in 2D materials at my grad school, and then I extended that to the magnetic 2D materials in my postdoc a little bit. And since 2019 fall, I'm an assistant professor at San Jose State University, and I'm establishing a research group focused on various properties of materials, such as electronic properties and ionic properties of materials for energy storage applications. So 2D materials is one of the main research project I'm working on. Just to give you a brief background on 2D materials, I hope everyone is familiar with graphene. So after Andrew Geim and Novoselov, they successfully experimentally exfoliate and characterize graphene, and there is huge interest in this field. And this graphene is just a single layer exfoliated from graphite that you can see here. And this is a wonderful material, but its band structure, if you see here the right plot, it's a metallic, so not very applicable for all electronic device application. It can be used as a contact material, but not as a channel material. Then research community started looking into other 2D materials that has sizable band gap. We have a lot of 2D materials now. Their ranges from metal to semiconductors. And you can see some of the examples here. Boron nitride, which is insulator, and transition metal dichalcogenides. It ranges from metal to superconductors. And we can also have elemental 2D materials such as black phosphorus, or we can have compound those 2D materials. And if the materials has the magnetic element in it, such as chromium or vanadium or iron, then we have extra knob to tune the properties. We can also have metal oxide in a layer system, such as here. It can also be exfoliated into single layer or few layers. So what is the common in all those materials is strong in plane covalent bonds and weaker out of plane van der Waals interactions. Because of this van der Waals nature of bonding, it's easy to exfoliate into single layer. So it has multiple applications. You can see novel device applications that I listed here. It can be in electronics, optoelectronics, piezoelectric, thermoelectric devices, energy storage, since it has intercalating properties for lithium, so it can be used as energy storage devices, and also sensors, catalysis, and lubricant. So most of them are potential applications, but catalysis and lubricants, it's already available in market based on one of those 2D materials, such as molybdenum. And another application is catalysis or lubricants in space applications where we want solid lubricants. Then these are the good candidate materials, since those layers are slide easily, and that can provide good lubrication to space applications. And if we have this magnetism in it, then it has additional functionality, of course, additional complexities, and we can have novel devices such as magnetoelectric devices, information storage, or spin transistors, or even 2D magnet. Okay, brief introduction on this TMD, transition metal dichalcogenides. As name says, it has transition metal in it, and then we have chalcogens such as sulfur, selenium, or tellurium. And based on this periodic table, different composition, we can see, let's say group 6 with chalcogens, it forms these electronic properties. Since those transition metal, they have different number of d electrons, so it's a crystal field effect, gives us this kind of electronic properties. So group 6, we can see it's semiconducting, so it's very useful for electronic device applications. But if you use other columns, we have metallic, nature, semi-metals, and so on. So their structures are stabilized in 3 different forms. So it can be, it's a hexagonal symmetry similar to graphene, but it's coordination between metal and chalcogens. It can be trigonal prismatic coordination, or octahedral coordination, or distorted octahedral coordination. We have seen in research more than 100 of TMDs investigated since 1960s. So this is not like very new materials, but the research started after the discovery of graphene, looking into single layer properties on those materials. Okay, so as I listed here, some of them are metals, some are semiconductors, and some others are superconductors as well. Okay, so not only that, there is stacking, how they stack together. They have different structures and corresponding properties. So we can see here this one 2H structure that we can see those chalcogens sitting on top of metal. So there can be many variations of this stacking. So altogether, we can see 11 polytypes in TMDs. And the right figure, it shows that can be fabricated, or that can be synthesized, or that can be transferred from one phase to other by different growth conditions with the temperature. So what it says is we have a lot of different types of structures. It provides us tunability of structure and properties for various applications. So not only that, since in reduced dimension, if we have a single layer, then there is a reduced screening effect. So if we place that in any medium, let's say a high dielectric constant medium, then there will be a screening by dielectric medium that will impact electronic and optical properties. And we can create heterostructures. It can be for transistor type applications where we can have metal and TMD interface or metal and oxide interface, but we need to understand the nature of that interface so that it can be applicable for various devices. And the right part I'm showing here, this is new area of physics. It's called twistronics. So if we have this heterostructure and if we twist, and we can see this fancy Moire pattern, and its corresponding electronic properties will be changed. So we have a lot of tunability in those materials. Okay, so to study those single layer properties and also the ball properties and heterostructure, what we use is a computational tool. It's called density functional theory. And actually, Walter Kohn and John Pople, he got a Nobel Prize in chemistry in 1998 regarding this density functional theory. So using different packages and codes, we can look into various properties. Okay, so we can look into defects and defect passivations and oxidation, area stability of the systems and interface properties, and also mixing those to tune the properties. And we will plan to include more than molybdisulfide, all other magnetic and non-magnetic materials, heterostructures. So I'm open for collaborations with experimentalists or any theoretical or computational group that does different than myself. So I'm happy to answer if you have any questions. Thank you.
Thank you, Santosh, for your interesting talk. Our next speaker is Liz Kyonka from CSU East Bay from the Department of Psychology.
Hi, everyone. Thank you for having me. I'm just going to share my screen in a second. Okay, so like Frank said, I'm Liz Kyonka. I'm an assistant professor at CSU East Bay in the Department of Psychology, and my specialization is the experimental analysis of behavior. A little bit about me. I was born and raised in Toronto, Canada. I went to undergrad at Brown University, where I studied rats and mice and did an honors thesis on interval timing in rats and graduated with a Bachelor of Science in Cognitive Neuroscience. I then moved across the country and across the Pacific Ocean to the University of Canterbury in Christchurch, New Zealand, where I studied pigeons for my graduate work. And because I had come in with some interest in timing, and my doctoral thesis advisor studied choice behavior, I looked at the dynamic mechanisms of choice and temporal learning. After that, I got a faculty position in the behavior analysis program at West Virginia University in Morgantown. So I moved across the Pacific Ocean again and set up a lab studying choice adaptation and behavior dynamics generally in pigeon models, mouse models, and eventually in human operant models, mostly working with convenience samples of psychology students. I then had an opportunity to work with a colleague of mine who was starting up a behavior analysis program at the University of New England in the very small town of Armidale in New South Wales, Australia. So with the idea that we were going to start one of the first behavior analysis programs in Australia, I moved across the Pacific Ocean again. So I think we're up to 3 trans-Pacific moves at that point. I set up a lab doing rodent research. Because we were a rural university, many of our students were online. So in addition to doing human subjects behavioral research on campus, I also started doing some online research and started teaching online. And not too many years after I got there, the university restructured and the behavior analysis program became something that was not going to happen, something that got lost in the restructure. And so rather than stay in rural Australia and teach introductory statistics to psychology students for the rest of my life, I moved back to my hometown of Toronto and spent some time doing some curriculum development for an online program at the Centre for Addiction and Mental Health, which is the largest research hospital in Canada. And then at the very start of the pandemic, I got this job. So my husband and I moved what I think has been one of the smallest moves yet, only about 4,000 miles from Toronto to Hayward, where it turned out the instructional design and online teaching work I'd been doing at CAMH came in very handy, because I've been teaching online the whole time that I've been here, with a plan to start collecting human subjects data as soon as it's reasonably safe to do so. When I'm not teaching, I like doing sort of slow things. I'm a slow runner, a slow hiker, and also a slow knitter, although I've been getting much faster at knitting. I really like knitting toys because they tend to be very well received. I knit clothes for myself, and it's pretty rare that I don't wear something that I knit. And so I knit this, but not this. And that's what I do. That's what I've been doing since I've been sitting around the house during the pandemic. Right. So like I said, I'm an experimental behavior analyst. That's a kind of psychologist that, or in my case, a psychologist that describes and explains the fundamental principles of the behavior of individual organisms. And as you can see from this word cloud of the titles of my talks and publications from 2013 to 2017 or thereabouts, a lot of the fundamental principles that I have been studying have involved time and choice, and it's mostly been with pigeons, although the word human is relatively large in that word cloud as well. But since I have shifted, in the recent past few years, my research interests have shifted to include some more translational topics of social significance. And the way that I tackle topics of social significance is through laboratory analogs. So for example, if I talk about a gambling analog, I'm not trying to duplicate all of the stimuli and consequences of a casino inside a laboratory. Instead, what I'm doing is establishing an artificial simplified situation that allows me to investigate some of the behavioral processes that are involved in a controlled environment. I thought I would talk about a couple of my ongoing projects. One on behavioral mechanisms involved in gambling and probabilistic choice. I started doing this in my pigeon lab at West Virginia. I continued it in Australia, and I think it's at a point where I hope we're going to do some exciting stuff as soon as we can have people back in the lab. And the other project is related to the title of my talk, working on developing effective behavioral interventions to modify technology use, with the idea being that I'm less interested in pathologizing specific patterns of behavior than in recognizing what patterns of behavior are associated with things that people want to change about the way they use the internet, the way they play video games online, and the way that they use social media. And how do we give them tools so that they can change those behaviors themselves? So my research on behavioral mechanisms involved in gambling and probabilistic choice, like I said, started when I had a pigeon lab with a couple of my graduate students. I worked to develop a pigeon slot machine analog. And one of the first things we did was assess whether pigeons could discriminate between different types of trials. So one of the interesting phenomena within gambling research is a sensitivity to what are called near misses or near wins. And so the idea is that if you play a slot machine and a cherry is a big win, you get some money, then a cherry lemon is actually a loss, you don't get any money, but people seem to react to it differently as if it's a win. But getting that effect in the laboratory has proved difficult. We were able to establish that we could do it in pigeon models, and that pigeons will choose alternatives will choose probabilistic alternatives more when gambling is when near wins are present. So the next step was to reverse engineer our pigeon analog into a procedure we could use with human subjects. I tried that with a bunch of different postgrad students in Australia. And the one that worked the best, I'm still kind of fine tuning it, was a repeated bet and collect task that we're writing up now. So now that we have more or less the task that we want, I'm pursuing some foundation funding to do a parametric investigation of brief mindfulness interventions on probabilistic and impulsive choice. There's lots of evidence that suggests that sometimes a brief mindfulness intervention, like a guided meditation or a breathing exercise, will affect people's choice. But there's also evidence that says that sometimes it doesn't. So I want to figure out, does it have something to do with the people, the task that you're using to assess the choice, or the nature of the intervention that you're calling a brief mindfulness intervention? Then once we figure all that out, what's the behavioral mechanism? Then, like I said, the other project that I'm focusing on now involves modifying technology use. This started with a review of treatment research that I did while I was at CAMH. The plan was to do a direct observation, to play naturalists and kind of develop ethograms and build a laboratory analog from there, which would enable us to identify consequences that maintain gaming and internet use, and to develop viable, effective, and empirically validated techniques for changing gaming and internet use habits, and then questionnaires to help people recognize why they play video games and use the internet, with the idea that the answers to their questionnaires would provide recommendations about what they could do to change their behavior. Because of the pandemic, that didn't work. So we started with the questionnaires, and I'm out of time, so I will just say that pilot data that we're still in the process of collecting indicates that a lot of people actually do want to change the way they use social media. My convenient sample of psychology students said that they estimated that they spend about 15 hours per week using social media, but it turned out that there was no correlation between how much they use social media and measures of dependence or wanting to change their behavior. We looked at 6 possible functions, and I was kind of surprised. 4 of them were endorsed by a large portion of participants. All right, thanks very much for your time. If you're interested in human-computer interactions, I'm building the functional assessment of social media and other forms of technology use into what I hope will be an NIMH R15. And I'm interested in collaborating with other folks who are doing work on human-computer interaction or behavioral addictions generally.
Great, thanks, Liz. Our next speaker is Wing To from CSU Stanislaus. from the Department of Physics. Wing.
Thank you, Frank. I'm just going to set up my share screen. Screen 2. Hopefully everyone can see that. Okay. Hi, so my name is Wing Tu from CSU Stanislaus. I've been an assistant professor here for 4 years, well, starting my 5th year. And first of all, I'd like to thank Frank and Monica for setting up this event and for all of you for spending an hour to listen to us talk about our research, and hopefully we can collaborate together at some point. Just my personal introduction is a little bit, well, let me just maybe tell you about my path into academia. So all of my, college and grad school time, I was known as a non-traditional college student. And that's because my parents actually brought me over to the US illegally in 1989. Eventually, we got our status fixed, but it took about 22 years for them to get their immigration visa. And by that time, they actually just wanted to retire in Hong Kong. That's where I was born. So the reason I was actually able to go to college is because of in California in 2001, there was a passage of this bill called AB 540, which allowed students who graduated from California high school to go to college with in-state tuition fees. And this is actually something I just checked yesterday when I was writing this talk. So if a student was not, if there wasn't AB 540, a student who was attending Stan State would have to pay $30,000 per year for tuition in order to attend a state college, which, even if you scale back the inflation to 2001, there was no way for me to afford that. And so I'm really appreciative of the California public school system, and specifically the college public school that allowed me to get to where I am today. So after completing my associate at Citrus Community College, which is down in Los Angeles, I transferred to UC Santa Barbara and finished both my bachelor and my PhD there in 2006 and 2012 in that order. And I actually finished my PhD in experimental particle physics, but today I'm going to talk to you about wildfire research, which is something that I transitioned to after coming to Stan State. And I just feel really privileged to be able to work at Stan State, because since I've been at Stan State, I was actually able to work with 2 DACA students who are both in graduate school right now. And also, there's also one AB 540 student who I'm working with right now to see if he can actually go to graduate school, because there is a weird gap. If you come to the United States at a certain time, you don't qualify for DACA, but you qualify for AB 540. So this is something that I'm going to work on with him. So let's talk about wildfire research. Let's go to the next slide. Okay. So I think I don't have to justify the need for study of wildfires, especially in California. I mean, it's all over the world. They have become more severe and more frequent due to climate change. And the current model utilizes the terrain, of course, that's very important in modeling wildfires. And also like the fuel source mapping, meaning if you're on a particular hill slope, right? What is actually there? Is it a forested area? Is it dry vegetation? Is it just rocks, right? What is actually there? And also meteorological measurements, which is taking into account the wind, the temperature, the humidity. And all of this is actually wrapped up together in this software package called Weather Research Forecasting Model that was actually developed by NCAR, National Climate Research Group in Colorado. And this is coupled with this thing called S-Fire now. They keep changing the name, but the idea is that we want to couple fire with weather, right? Because, when there is a fire, the weather affects the fire in a tremendously. And, depending on the wind direction and also the humidity, it changes the path of the fire and also the amount of smoke, the heat. And specifically what we want to do as a starting project is actually study the fire from last year, which is actually close to date. So the Creek Fire, so there's a map on the here on the right. So it's just so people can orient themselves. So down south is Fresno. To the west here is actually where I am in Turlock. So this is the Sierra Nevada to the right here. So if you look up to the top of the map here, Yosemite National Park is up top there. So just so for people to orient themselves. And this is the picture of the fire last year. So in this path of research, what I started doing is actually working with a postdoc at Lawrence Livermore National Lab. And her niece is actually on the fuel source mapping. So I'm trying to tackle like one little piece of it at first, but hopefully we can expand on this in the future. So the way we are trying to map the fuel sources in the Sierra Nevada is by using satellite imagery. Okay, so this is on the right here is a satellite image of the same map that I just showed you in the previous slide. So the fire is actually between the 41 highway and the 168 labeled here. So it's actually up here somewhere. Okay, and the idea is that, well, if we can actually have a more updated map of the vegetation, the soil, and the dry grass in the area, we can actually make a much better predictor of what happens if a spark happens here again. And the way we, test this hypothesis is by, using the historical fire. But in the future, the hope is that we can actually make these predictions for any fire, where, if you just have a map of California, if I start a fire here, what happens? That's the hope at least. So the image on the right is actually taken on September 3rd. I think the Creek Fire started the day after on September 4th. So I'll actually show you an image of that. But before we talk about that, what I'd like to tell you guys is like what kind of satellite image are we using here? So we decided to use this Sentinel-2 data set, which is actually satellite data taken by the European Space Agency. The reason for this, it has a 13 band, meaning it actually looks at 13 different wavelengths of light that's coming from the planet. And it takes a picture of the area every 10 days. So it's actually really nice because you can just keep getting updates of where the vegetation are. So you can actually have the most updated or even figure out what the evolution is for that particular area, before and after fires, or if someone is, building a road or making a little town there. It doesn't have the best resolution, so it has a 10 meter by 10 meter resolution. So, you can see things, at maybe the size of a small house. Okay. So, but to show you guys the power of this 13 band, let me just show you what it looks like after the fire started. So this is the satellite images taken on the 13th. So 10 days later, because it takes the satellite 10 days to cycle through the entire planet. Okay. So in image, RGB image, you can see that the entire area is just covered in smoke because there is a fire there. But if you look at it in what's known as a shortwave infrared, which is very far into the infrared spectrum, it's almost like a radio wave. You can still see a lot of structures. So this is one of the power of the Sentinel-2 data, is because not only do you get the satellite imagery in color, but also in infrared also. So the way we're tagging these area is by taking the spectrum data of the satellite image, and basically the idea was for us to train a artificial neural network. This another fancy word for like machine learning or AI. So the main idea is that we want to be able to train these artificial neural network so that the computer can start doing the tagging themselves, as opposed to right now we actually have about 5 students just doing looking at the picture and then looking at the spectrum in order to figure out whether or not something is soil, something is green vegetation, or something is dry vegetation. And you can tell that they have very different shapes in each of the categories. And And having this enhanced, infrared imagery is actually really useful. Our campus also recently gave me a grant to buy an aerial drone. So a lot of times with 10 meter by 10 meter resolution, you may not be able to tell whether or not one is something is the other, but hopefully we can actually use the aerial drone to just take aerial image close up and figure out what things are, okay? So what I want to do is just wrap up and tell you about the future work we're hoping to do with this path of research. We are working on this WRS S-Fire, this complicated acronyms for simulating what happens in a fire if a spark does happen in a particular place. And we'd like to enhance this by using either AI or machine learning technology that I used before in order to make a more accurate and faster simulation. Because right now what happens is that typically it takes like a year and a half for someone to analyze the fire and figure out what actually happened, how to be able to re-simulate a fire that already occurred. And the hope is that, eventually maybe, if we just put a fire at any point in California, you can actually predict the path and the atmospheric effects. And so the faster simulation could lead to these real-time burn path analysis. So the current collaboration is actually just mostly me. I'm working with 2 research scientists at Lawrence Livermore Lab who are actually just kind of advising and guiding me, but I have a lot of undergraduate, both in physics and computer science. And the on-campus grant I actually mentioned before, we're planning to hire geography and more computer science students. So it's highly interdisciplinary. And I'm hoping for collaborators in atmospheric, environmental science, fire science, geography, computer science. So thank you for your time. I think we're supposed to end and have our discussions after.
Great, thanks Wing and all our speakers today for very interesting talks. We now open it up for anyone to ask our group of presenters questions. So I will open up to the floor for Q&A. Don't be shy. And if you want to share your screen, that'd be great too. So the floor is all of yours.
For Dr. Wang, what kind of processing speeds do you need to be able to do more real-time analysis?
That's hard to gauge. So right now, the WRF S-Fire framework solves like hundreds of differential equations. So in order for me to, let's say, resimulate the creek fire, for example, typically it will take like 6 months of processing time, not just writing the stuff. So just, having a compute, maybe having like 500 computers working at it for multiple months. So the hope is that with AI machine learning, instead of solving those differential equations, you're actually using the data to predict what's going to happen in the different data set, and instead of solving all these differential equations. So the hope is that we'll be able to speed this up, maybe by a factor of 10, maybe by a factor of 100. And if we get to a factor of 100, you could do real-time simulation, because you could take just a day for you to get the results.
So in the same sort of sense, it's been done quite accurately for hurricanes and other kinds of systems. And those are done, with a high level of accuracy. So what's the difference between hurricane modeling, which is used all of the time and is extremely commonplace, and a fire model, which you would assume, it's based on thermodynamics and the physics of the local environment, wind direction, and this type of thing. So where's the big gap in knowledge that keeps us behind?
I think knowledge-wise, it is not keeping us behind, is that you're dealing with just a more complex system. So like when hurricane develops, they develop over oceans, which has a much simpler topography than the Sierra Nevada, for example. And also the fuel source for a hurricane is just the heat from the ocean, right? So you can measure that where the fuel source can change, at our resolution, every 10 meters, every 100 square meters, there could be a different fuel source. And then if you go over a hill, and there could be a difference in how the path of the fire travel. And also right now there's actually this S-Fire model that they're working on actually is also going to include the moisture of the soil, which actually our some collaborator at San Jose State is trying to go around and measure the soil moisture level all over the place in Northern California. So there's it's just a more complex problem. You may see that like especially when the hurricane go over land, it just does things that we don't expect, right? And I think that complexity is sort of built in all the time with fires.
So hurricanes are kind of boring when over water, but when they're over land, they have they're like Sybil. For those that I kind of age myself there, they have a variety of different personalities. So what you're saying, a fire is more like Sybil than a hurricane that's above water. That you have all these different variables, and a simple COMSOL-like type of analysis is not going to. You can't use some sort of prepackaged type of COMSOL type of thing because there's just so many different variables.
Right, and the complexity level goes up, and this WRF S-Fire package does do that to maybe about within 10% of accuracy, but it just takes a long time to compute right now. That's one of the things we want to enhance. It's just to reduce computing time using data-driven method versus these solving a bunch of different equations, see where the air packets that would be there at a certain temperature would travel with their certain amount of moisture, with a certain amount of heat.
So questions out there? So Liz, I had maybe, I won't say a difficult time, but trying to understand the correlation between pigeons and gambling. Try to help me understand that a little bit better.
So within the scope of a 10-minute talk, outlining the procedure that's used to set up a gambling analog for pigeons would be a little bit difficult, but the very basics of it are that we put pigeons in an operant conditioning chamber, which is just a little box, and we present stimuli, different colored lights, and the response devices, the input devices, are these little discs that they peck. And the program is designed so that if they satisfy the requirements of the schedule, it provides them with access to food. And so we had the basic procedure, the stimulus procedure was that they would get 3 lights. So they'd see 3 lights in sequence. So 3 red lights in a row would be like 3 cherries in a row. And that on trials, when they saw 3 red lights in a row, they'd get food, some amount of food. On other trials, they saw nothing, but some trials were unlike the 3 red lights, they were 3 green lights in a row. So maximally unlike the 3 red lights. Some of them were maximally similar. So they get a red light, and then a green light. we'd measure their response latency and other facets of their behavior. And what we get is a difference in the timing of responding that indicates that there's a meaningful difference, or there's a difference in the pigeon's behavior based on what type of trial they got previously and what's the current trial. Right? We then embedded that task into a choice task. Right? So they could choose between, do you want this set of outcomes, which a certain set of outcomes, right? So if they peck the left key at the choice point, they get a little bit of food for sure. Or if they peck the probabilistic key at the choice point, they might get no food, or they might get some food. And in some conditions, it was more food than they'd get if they chose the certain key. So then the manipulation was, did we include these cherry, lemon trials in the probabilistic outcome or not? Was it all just red versus green? And it turned out that when we included the near wins, the cherry, lemon, pigeons would choose that probabilistic outcome. They'd peck the probabilistic key at the choice point. It was about 2.6 times more often than they'd peck the certain key, whereas they were pretty indifferent if the near wins were absent.
So pigeons are that smart, huh?
Oh, pigeons can do anything. Yeah. Actually, part of when I was a grad student 100 years ago, I kept doing experiments and making the choices that they had to make like that much more sophisticated, that much more sort of nuanced, that much more dynamic, trying to see like at what point do they break and give up, and they just never. I graduated before I got to the point where it was too complicated for the pigeons.
Very interesting. Very interesting. So any questions out there? Hearing none, I'm going to give all of you some time back. Before we leave, I'd like to thank our speakers for presenting, and very enjoyable talks. Thank you. And hopefully this might lead to a collaboration or two in the future. I want to remind you of a few coming events. October 1st, we have our NIH-funded CSU Institutional Training Grants and Research Education Programs webcast. That's at 10 a.m. on Friday, October 1st. Our next virtual research cafe is Friday, October 15th at 11 o'clock. So I thank you all for attending and look forward to seeing you again at a future STEMnet event. Take care and have a wonderful weekend.